this lecture, I'll prove the Krull-Schmidt theorem. So the theorem says, let M, R can be any ring, let M be an R module satisfying the ACC and the DCC. Well, we know already that such R modules can be written as a direct sum of indecomposable submodules. Now suppose we have two such decompositions. Suppose M equals M1 direct sum MK and N1 direct sum NL are decompositions of M into indecomposable submodules. Into direct sums of indecomposable modules then K is equal to L and there exists a bijection sigma 1 to K to 1 to L such that N sigma I is isomorphic to Mi for all I between 1 and K. In other words, the direct summands in this decomposition are uniquely determined up to reordering of summands. The proof will use the locality of the endomorphism algebra and also use the calculus of projections. So the proof will proceed by induction on K. If K equals 1, there's nothing to prove. M is indecomposable. And so N itself must also have only one summand. Okay. Otherwise, let's assume that K is greater than or equal to 2. Okay, now we have these decompositions. Let identity of M equals P1 plus Pk and Q1 plus QL be the partitions of unity associated to the two direct sum decompositions, which maybe I can give them names 1 and 2. Respectively. Okay, so now let's look at P1. Well, P1 is P1 times identity of M. But then identity of M has a decomposition. So it's Q1 plus Q2 plus QL. So P1 Q1 plus P1 Q2 plus P1 QL. Now P1 restricted to M1. Okay, P1 anyway its image is contained in M1, so we can think of P1 restricted to M1 as an element of and are M1. Okay, and by the theorem which I proved in the previous lecture, this is a local ring. And what we have is that the identity of M1 equals P1Q1 restricted to M1 plus P1QL restricted to M1. Now I claim that P1QJ is an isomorphism or maybe I should say P1QJ restricted to M1 is an isomorphism from M1 to M1 for at least one J. Why is that? Well, this whole thing is happening inside end R M1. And this end R M1 is a local ring. And so if none of these summands were isomorphisms, then by the theorem that we proved in the last lecture, they would all be nilpotent. And so, and their sum also would be nilpotent because all these nilpotent elements, they form a two-sided ideal. But then the sum is the identity, which is clearly not nilpotent, so it's a contradiction. So P1QJ must be an isomorphism for at least one J. And so let's assume without loss of generality that P1Q1 by renumbering is an isomorphism. Okay, so what we have is we have M1, so I should say P1, yeah, so we have M1 and then we have M1 and we have this isomorphism P1Q1 raised to restricted to M1. And we can look at P1, so Q1 goes from, if I take Q1 restricted to M1, it goes to N1 because the image of Q1 is contained in N1, and P1 restricted to N1 goes back into M1. And what we are saying as this composition is an isomorphism. Now I claim that Q1 P1 restricted to N1 is also an isomorphism. Why is that? If not, since N1 is indecomposable, and Rn1 is also local. And in fact, by the theorem in the previous lecture, what we have is Q1 P1 restricted to N1 to the power N is 0 for some N greater than 0. But now what you can do is you can multiply this on the left by P1 and on the right by Q1. And what you'll get is P1 Q1. So here you multiply it by P1 restricted to M1, and here you restrict Q1 restricted to N1. So what you'll get is P1 Q1 restricted to M1 to the power N plus 1 is equal to 0. But that contradicts the fact that P1 Q1 is an isomorphism. So now since P1 Q1 restricted to M1 is an isomorphism, we have P1 restricted to M1 is surjective. P1 is surjective on P1 is surjective onto P1 restricted to N1 is surjective onto M1, and we also have that Q1 restricted to M1 is injective. And therefore P1 restricted to N1 and Q1 restricted to M1 define isomorphisms between M1 and N1. So M1 is isomorphic to N1. Okay, so we found from these decompositions, we've been able to pick out one summand from the first decomposition, one summand from the second decomposition that are isomorphic. In fact, we just renumbered the second decomposition to make that the first summand. So what we have is that M1 is isomorphic to N1. Now for induction to kick in, it suffices to show that we will show that M2 plus Mk is isomorphic to N2 plus Nk. That's not really obvious yet. So let M prime be just the sum N1 plus M2 plus Mk. What I mean is just you could just put plus here, but this part of the sum will be direct, and this part this is a submodule of M. Now if N belongs to N1 intersect M2 plus Mk, then what we have is that P1N has to be 0 because P1 vanishes on M2 direct sum Mk. But recall that P1 restricted to N is injective. It's an isomorphism onto M1. We get that N is equal to 0. So this N1 intersect M2 direct sum Mk is 0. And so we have M prime is N1 direct sum M2 direct sum Mk. Now I want to show that M prime is actually equal to M. We can do this by comparing lengths. Length of M prime is length of N1 plus length of M2 plus length of Mk. Okay, if you have a Jordan-Holder series for each summand, you can combine them to get a Jordan-Holder series for the direct sum. And this is equal to, well, N1 is isomorphic to M1, so the length of N1 is equal to the length of M1 plus length of M2 plus length of Mk, but that is equal to the length of M. So since M prime is a submodule of M with the same length as M prime must be equal to M. So what we have is M is N1 direct sum M2 direct sum Mk, and M is also M1 direct sum M2 direct sum Mk. So it follows that M mod n1 is isomorphic to M2 direct sum mk, but also by the decomposition 2 that we had up here, it follows that M mod n1 is isomorphic to n2 direct sum nl. By the decomposition 2, and therefore M2 direct sum mk is isomorphic to n2 direct sum nl. And so the induction hypothesis on k kicks in, and so what we get is k minus 1 is equal to L minus 1, which is just the same as saying that k equals L, and there exists a bijection from 2 to k to 2 to L such that n sigma I is isomorphic to mi for each I for 2 less than or equal to I less than or equal to k. And putting that together with the fact that m1 is isomorphic to n1 proves the Krull-Schmidt theorem for m.